Welcome everyone, and thank you for joining us on today's webinar, Realizing Better LNG Product Transfer Measurements with Coriolis Meters. My name is Allison Sterling. I'm a Marketing Manager at Emerson, and I'm pleased to welcome you to our Emerson Full Expert webinar series. Before we begin today, I'd like to just take a brief moment to acquaint you with your webinar environment. On your screen, you should be seeing a presentation window on the left side that currently has our title slide, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box with related content where you can view and download them during the event. You can also resize, move, or minimize any of these windows during the event to fit your viewing preferences. Also, at the bottom of your screen, you should have a row of icons where you can have some added capabilities, such as being able to share this webinar via social channels, or you can also request a visit from one of our flow experts. Throughout the presentation, we encourage you to interact with our speaker by typing in questions and comments using that Q&A chat panel, and we will be collecting all the questions and answering them at the end of the webinar. We are also recording today's session, and we will make a link to this recording as well as links to the related resources available to you tomorrow via email. On today's webinar, we are lucky enough to have joining us Mark Butler, our Oil and Gas Midstream Industry Manager at Emerson Micro Motion. As I just said, Mark is the Oil and Gas Midstream Industry Manager, and he is responsible for representing customer needs for oil and gas pipeline, gas processing, and terminal applications. During his 28 years with Emerson, Mark has held a variety of manufacturing, engineering, and global marketing positions. Mark has also worked as a physical scientist at the National Institute of Standards and Technology, or NIST. He holds a BS degree in mechanical engineering from the University of Colorado. Welcome, Mark.
Well, thank you, Allison. It's good to be here. Hi, everyone, and thank you for joining us today. We're going to start by quickly reviewing some of the fundamental aspects of liquefied natural gas, more commonly known as LNG. Then we'll cover some of the different methods for measuring quantities of LNG. Next, we'll focus on some of the best practices and unique advantages of measuring LNG with a Coriolis meter. And then we'll finish with an update on some of the latest developments in the testing and certification of LNG flow meters. LNG is a cryogenic fluid. It is made by cooling natural gas to a liquid state at a temperature well below the range of normal ambient temperatures. NIST Handbook 44 defines a cryogenic liquid as any liquid that is at a temperature below -243 degrees Fahrenheit. LNG qualifies as a cryogenic liquid because it's normally at or below a temperature of -260 degrees Fahrenheit, or in centigrade -162 degrees. Although LNG can remain as a liquid at higher temperatures if the pressure is high enough, this is typically not the case, as LNG is normally stored at low pressure, around the neighborhood of 5 psig. The density of LNG is a little less than half the density of water, which makes it about 600 times more dense than natural gas at reference conditions. Herein lies the benefit of LNG. We can store and transport about 600 times as much LNG in the same space that it would take to store the gas that was made to use the LNG. Even compared to compressed natural gas, when it's at a pressure of 3,600 psig, the density of LNG is about double. A quantity of LNG is commonly represented in units of mass, in pounds or kilograms, but it is also common to state the amount of energy that is contained in the LNG. To determine the amount of energy, a calorific value or a heating value that tells us how much energy is in each pound or kilogram or standard cubic foot or normal cubic meter of LNG is used. Another useful indication of the energy content of LNG is the Wobbe index, which is just the heating value divided by the square root of the specific gravity of the LNG. Another new concept for indicating the quantity of LNG is called the diesel gallon equivalent, or DGE for short. The DGE is defined as a mass unit equal to exactly 6.059 pounds, but it also carries with it an implication of the energy content by suggesting that the energy within 1 DGE of LNG is approximately the same as the energy that is contained in an average typical gallon of diesel fuel. The DGE is estimated by assuming the average density of both LNG and diesel fuel, the average energy density that is. In reality, the DGE implication of energy quantity is only a rough estimate of the energy because different mixtures of LNG will have different compositions and different energy densities, which is also true for diesel, but the mass of the DGE of LNG will always be exactly 6.059 pounds of mass by its legal definition. There's one final attribute of LNG that is important as a fuel, and that is the methane number. The methane number for LNG is analogous to the octane rating of gasoline in that it gives an indication of the probability that the engine that's using the LNG as fuel may experience knock, or premature combustion of the fuel. The methane number is important as a quality measure, but it has no direct bearing on the mass and or energy quantity of the LNG. So LNG is mostly methane, but just as is the case with natural gas, the composition of LNG is really a mixture of many different hydrocarbons and some other inert gases. The proportions of these components in LNG can and will vary significantly from region to region, mainly because different global markets actually have different expectations and specifications for the energy density of LNG. Moreover, the composition of the natural gas that was liquefied to make the LNG will vary depending on the region where it was produced. Richer LNGs have a higher concentration of the heavier hydrocarbons like propane and butane, whereas leaner LNGs will have fewer of these and more methane. In some cases, rich and lean LNG are blended together or with propane to bring the LNG to within a target heating value specification for a specific destination market. Ultimately, because the composition is uncertain and can vary enough to make the specific gravity of LNG vary by as much as 12%, volume measurement of LNG cannot be done reliably and corrected to either mass and or volume at reference conditions. Volume measurements of pure cryogenic liquids like nitrogen, argon, and oxygen, whose compositions are very consistent and well-defined, are much easier to convert to mass and standard volume units. I mentioned earlier that LNG is stored at low pressure. This saves capital infrastructure costs by avoiding the need for high-pressure designs for the piping, tanks, and other system equipment. Storing LNG at low pressure actually works quite well because of a process called auto-refrigeration that is used to keep the LNG cold enough to keep most of it in liquid form. This is accomplished by the simple act of venting LNG that has vaporized from the LNG in the storage tank so that the pressure inside the tank does not increase. LNG that vaporizes is called boil-off gas, or BOG, and allowing the boil-off gas to vent actually cools the remaining LNG to keep it at or below the boiling point. If the pressure of the boil-off gas inside storage were allowed to increase, it would heat up as it compressed and auto-refrigeration would not occur. The LNG would boil off much faster in this case. Part of the challenge of venting the boil-off gas is what to do with it. It is undesirable just to let the boil-off gas vent to atmosphere because that both wastes the LNG and it also allows volatile organic compounds to pollute the atmosphere. This is part of the reason why LNG is better suited as a fuel for vehicles that are constantly consuming the fuel than it is for personnel automobiles. Vehicles and vessels that are in operation continuously aid in auto-refrigeration because the boil-off gas is taken from storage and burned as fuel. Vehicles that need to remain parked for a long time with no fuel consumption would quickly lose the LNG to boil-off gas. These types of vehicles typically will use CNG instead because CNG can be stored at high pressure without auto-refrigeration. Some of the various common applications where LNG is transferred between two parties are shown in this list. Many on-road vehicles, including trucks and autos, run on LNG, as do a growing number of rail locomotives. Marine vessels, especially those that most frequently operate close to shore where emission standards are strict, are switching to LNG fuel in increasing numbers. Cruise ships, ferries, and Jones Act cargo ships are some of these. Even ocean-going cargo ships and tankers need to eventually approach a shore in order to deliver and pick up their cargo. Vehicles and vessels that use LNG as fuel full-time or part-time all need fueling systems that can measure and report to them how much fuel they purchased. The exceptions are LNG tankers and transport vehicles that already have a ready source of LNG fuel to draw on in the form of the boil-off gas from the cargo that they're carrying. Other LNG product transfer applications include LNG tanker truck loading and offloading systems, delivery systems mounted on trucks that deliver LNG to multiple customer locations, jetties for loading and offloading larger LNG transport ships, blending systems, and even drilling rigs and mining equipment. Well, I want to take a second to pause now and ask a quick poll question. This is your chance to interact with us and each other. And if you're a consumer of LNG as fuel, please take a moment to select the type of equipment that you use most often that does consume LNG as fuel. And when you're all done, submit your answer by clicking on the button that says Submit at the bottom. You may need to scroll down in order to see this. And after people have voted, we'll review the results together. So just give everybody a second to vote. Seeing a few votes coming in. Very good. Well, hopefully everybody's had a chance. So let's take a look at some of the responses we've seen. Kind of all over the map, we see some on-road trucks, rail locomotives, marine cargo vessels, industrial equipment, and a lot in the other category. Very interesting. Okay, well, moving along. Now it's time to go over some of the different methods that are used to measure quantities of LNG. We'll start with the de facto standard for international trade of LNG, and that is tank gauging. So tank gauging determines the volume quantity that has been transferred by measuring the change in the level of the LNG in the tank and then calculating the change in the volume of the LNG from the strapping tables for the tank. There are a couple of procedural requirements that make the tank gauging method a bit costly and time-consuming and which may contribute to measurement uncertainty. It's important to wait until the level of the LNG inside the tank is stabilized before finishing the measurement of the total quantity delivered. And this may take some time depending on the conditions inside the tank. As time passes, while waiting for stabilization, boil-off gas can vaporize inside the tank, causing the level to change, even after the product transfer has stopped. With tank gauging, it is also necessary to limit the product transfers to one at a time because the change in the level that is observed should only be attributable to one product transfer in order for this method to work. With tank gauging, the density is computed from measurements of the fluid properties inside the tank using equations of state. This requires a knowledge of the LNG composition. Some of the challenge of determining the average fluid density is caused by changes in temperature, pressure, and composition at different levels and points throughout the tank. The measured change in the volume of LNG in the tank and the average estimated LNG density are used to then calculate the mass that was transferred. And then the energy is calculated from the mass quantity using the heating value of the LNG. There are some things to understand about the sources of uncertainty with tank gauging. First, the volume measurement requires two separate level measurements, both before and after the transfer. So all the uncertainties of each of these two measurements are combined to make the overall volume uncertainty. The level inside the tank needs to be stable at the time of both the level measurements, and if the temperature of the LNG is changing, the level will continue to rise or fall until the temperature becomes stable. Second, the strapping tables that equate the level measurements to volume have some uncertainty. If the tank is on board a marine vessel, trim and list of the vessel can add uncertainty and instability to the strapping tables and the level measurements of an onboard storage tank. Temperature and composition may vary at different levels and points within the tank, adding uncertainty to the average LNG density, and boil-off gases can occur during the transfer, making it appear that more LNG was transferred than was actually exchanged. The uncertainty of the measurement of the calorific value will, of course, translate into the uncertainty in the energy measurement. Weight measurements are also frequently used to quantify the amount of LNG transferred. Portable ISO containers and tanker trucks full of LNG can be measured on large truck scales before and after loading to determine from the change in weight how much mass of LNG was loaded. As with the tank gauging case, weight determination of quantity is based on the difference between two separate static measurements, the weight before loading, known as the tare weight, and the weight after loading. Conditions must be stable during both weight measurements for the total mass determination to be accurate. Energy quantity is determined directly from the mass measured with weighing, so there is no need to estimate the LNG density as there is with tank gauging. Weigh scales must be carefully maintained and checked periodically with traceable mass standards to remain accurate over time. There are some important sources of uncertainty in the weighing method to be aware of. Just as with tank gauging, because there are two separate measurements that must be made both before and after loading or unloading, the uncertainty of both measurements combine to add to the total overall transfer quantity uncertainty. If the process takes a long time because the transfer is slow or because stabilization of the scale takes a long time, then boil-off gas losses can occur that may result in error in the total delivery measurement. Wind and weather can play a large role in how long it takes for the scale indication to stabilize. Sometimes debris or animals can get into the scale pit and can interfere with the scale linkage, causing errors. If the truck has to drive from the loading point to a scale at a different location, then fuel consumption from point to point must be estimated and also taken into account. And as with tank gauging, any uncertainty in the measurement of the calorific value will translate into uncertainty in the energy measurement. Dynamic flow measurement is another way to determine the amount of LNG that has been transferred. Unlike tank gauging and weighing, the total transfer is determined by a continuous flow measurement that occurs as the transfer is taking place. With dynamic flow measurement, there is no need for waiting periods or stabilization at the beginning and or the end of the transfer, because as soon as the transfer is done, the measurement is also complete. Because the level or weight changes in the storage do not need to be measured when flow meters are used, it is possible to perform simultaneous multiple deliveries into and out of the same storage tank. Coriolis flow meters measure mass flow directly, so there's no need to estimate the average density of the LNG in order to determine either the total mass or energy of the transfer. Micro Motion Coriolis meters also have live diagnostics that monitor the state of the fluid and can easily detect an alarm if there is ever any boil-off gas or other vapor passing through the meter. The most significant limitations of Coriolis meters to be aware of is that they are limited to sizes of about 12 inches or 300 millimeters and smaller. Liquid ultrasonic meters, sometimes called LUSMs, are another good metering option for LNG, especially in large-scale operations that flow at rates that are too high to cover with even the largest Coriolis meters. Because ultrasonic meters measure in volume units, the average density must be measured or estimated to convert the total volume into mass units. Sources of uncertainty with flow meters are different for different types of flow meters. In general, every meter will have an accuracy specification, and it is important to verify with the manufacturer that the published accuracy does apply to LNG cryogenic measurements. If there is a possibility that the density of the LNG as it passes through an ultrasonic meter could be changing during the course of the transfer, either because the temperature, pressure, or composition is changing, then this must be taken into account in the average density. This is not an issue with the Coriolis meters because of the direct mass flow measurement. As with the tank gauging and weigh scales, any uncertainty in the measurement of the calorific value will translate into uncertainty in the energy measurement. In order to perform dynamic custody transfer measurement of LNG in energy units, measurements must be made of the LNG in both liquid and gas phase. The total mass of the LNG in liquid phase may be measured with a Coriolis flow meter, or the total volume of the LNG in liquid phase may be measured with an ultrasonic meter. If mass quantity is all that's required, then the meter is sufficient and no measurement is needed in the gas phase, although liquid density is still needed to convert the ultrasonic meter reading to mass from volume. If, on the other hand, the transfer needs to be quantified in energy units, then the calorific value or heating value must also be measured. With technology that is commercially available today, to make a measurement of the heating value requires that a sample or samples of the LNG must be vaporized into gaseous form so that a gas chromatograph or a gas-specific gravity meter, sometimes called an SGM, can be used. It is very important that the vaporization process be done with care and as fast as possible, because there are many opportunities during the vaporization process alone for the sample to be altered in a way that it will no longer accurately represent the LNG heating value or composition. Emerson has equipment that will facilitate the necessary vaporization process to ensure accurate results. Before I get into more detail on Coriolis measurement of LNG, I want to explain why LNG must be measured directly in mass units or else eventually converted into mass units. Transfers in units of mass are common today. Many LNG fuel dispensers sell LNG directly in mass units. The International Group of Liquefied Natural Gas Importers, called GIIGNL or GIGNL, publishes the LNG Custody Transfer Handbook, which contains a description of the following process to describe how major import-export terminals should measure LNG in energy units. The first step is to measure the total volume quantity, which is now often done by tank gauging. The second step is to determine the average density from the composition and temperature. The density is then used to convert the volume into mass units. If you have been using a Coriolis meter, you can begin the process at this step, since the Coriolis meter starts with a direct mass flow measurement. The gross calorific heating value is determined and used to convert the total mass quantity units into total energy units. In some cases where vapor that is displaced by the flow of LNG into the receiving tank is being returned to the LNG supplier, the energy content of the returned vapor is also measured and subtracted from the total amount delivered to yield the net total amount of energy that was exchanged. Only mass or energy units are used to communicate the total amount of LNG transferred. Because of composition, density, and heating value of LNG, the heating value can change so dramatically that the quantity measurements in units of volume and or standard volume are not generally used for custody transfer. Let's take another quick poll question. Please select the measurement method that your company uses most often to measure LNG for custody transfer. And remember, you need to click the Submit button to submit your answer at the bottom. Give everybody a minute or two here so we can see most of the responses. Starting to see a few responses. Okay, let's take a look together. We've got some tank gauging, weigh scales, mass flow meters, ranks higher than I expected, volume flow meters, and others. Very good. Okay, thank you, everybody. Micromotion Coriolis meters have a long history in a wide range of successful LNG applications around the world. The use of micromotion meters in cryogenic liquids and LNG measurement dates back over 20 years, and this experience includes the official certification and/or approvals of micromotion meters for custody transfer measurement of cryogenic liquids that was issued by NTEP in the US and MID in Europe. Micromotion meters have been used on LNG tankers for boil-off gas and engine fuel management. They were installed as early as 1999 in Australia by GasNet. And Micromotion Coriolis meters makes use of special patented temperature correction algorithms to improve the accuracy in the cryogenic temperature range. There are third-party test reports that document that the calibration of Micromotion Coriolis meters using water at ambient conditions, just like we do in our factory before shipping the meter, are valid for measuring LNG without any further adjustments. They have published accuracy of plus or minus 0.35% at cryogenic temperatures, and also ATEX safety approval down to minus 194 degrees centigrade. There are some valuable benefits to using Coriolis meters that are driving people to change from other measurement methods and technologies. For the most part, savings in time and cost are what they gain by switching, but an improvement in accuracy is also a benefit in certain cases. Having equipment and capability to make a dynamic measurement with a Coriolis meter helps LNG terminal, station, and fleet operators first and foremost by eliminating the delays and costs that they face with tank gauging and weigh scales because of the need to wait for stable static measurement conditions. With a dynamic measurement, at the moment product stops flowing, you already have your transfer quantity measurement. By relieving the storage tank from the extra responsibility of being a crucial traceability component of your custody transfer measuring system, you gain flexibility in the design and operation of the tank that will allow you to focus more on improving the performance of its primary function, which is to safely contain the LNG product with as little operating and maintenance cost as possible. Demurrage costs in marine loading and offloading are a particular ripe opportunity for operating cost savings that can be gained with dynamic measurement. Dynamic measurement of the boil-off gas vapor return line with a Coriolis meter can also help improve overall transfer quantity measurement accuracy. The same Coriolis meter design that can measure the liquid LNG flow accurately can also measure the LNG vapor that is being returned to the LNG supplier. A mass flow measurement of the LNG boil-off gas return line is one of the most accurate ways to measure and account for the energy of the vapor displaced from the receiving tank, as prescribed in the Gignal Handbook. Micromotion Coriolis meters give system designers more flexibility with the ability to measure flow in either direction through the same meter. Since Coriolis meters measure in mass units directly, they are ideal for measuring LNG in those applications where trade will be in units of mass, such as the applications that will be required to comply with NIST Handbooks 44 and 130, the Canadian Weights and Measures Act, and OIML R117. All three of these regulatory standards require mass units for sale of LNG. Other metering technologies that measure volume and/or velocity must convert to mass units to comply with any of these standards, and that introduces additional cost and measurement uncertainty because fluid properties must be measured and/or controlled so that the LNG flowing density can be known in order to convert from volume to mass units. Sometimes this can be very challenging for LNG because instruments to directly measure the density of LNG accurately are hard to find, while any other method of determining the density is complex and depends on many factors, each of which add uncertainty. When it comes to measuring transfer quantities in energy units, recall again that the heating value from the gas chromatograph might be in either units of energy per unit of mass or in energy per unit of standard volume. Remember also that there is going to be a greater uncertainty in the heating value with LNG because of the risk that the vaporization of the sample might alter the composition of the gaseous sample from the composition of the LNG. Bearing all that in mind, I want to give you some good news, which is that you can reduce the uncertainty by choosing to use the heating value that is in the units of energy per unit mass. If you look at the chart and compare the left side to the right side, you'll notice that each of the primary components of LNG have their own heating value when in their pure form. But on a percentage basis, they're far more different from each other if the units on the left of energy per unit of standard volume are used than if the units on the right of energy per unit of mass are used. This is caused by the fact that the heating value of each individual hydrocarbon component, when stated as energy per unit of standard volume, can vary considerably. On the other hand, the energy density per unit of mass is very stable from one component to the next. So the net result is that the changes in the composition of the LNG mixture will have much smaller impact on the heating value in energy per unit of mass than on the heating value in units of energy per unit of standard volume. The bottom line is that a Coriolis mass flow meter measurement will yield a more accurate energy measurement than a volume measuring meter will, especially if the composition of the LNG can be changing during the delivery. The best practices for using a Coriolis meter in LNG measurement are pretty straightforward. Most important, perhaps, is to work with the Coriolis meter supplier to select the perfect size Coriolis meter for your application. You don't want a meter that is too small because this will make the pressure drop across the meter higher than it needs to be, which may increase delivery system boil-off gases. And similarly, if you place a Coriolis meter on the boil-off gas return line, you want to make sure it is large enough to avoid creating unnecessary pressure drop across the meter and back pressure on the line, which could result in recondensation of the LNG. Neither do you want a meter that is too large, because the Coriolis meter will not be as accurate as it could be if you are flowing at a flow rate that is very low compared to the normal flow rates for that size meter. Make the most of the process diagnostics that the meter can provide. The meter is very good at detecting vapor bubbles and flashing in the LNG liquid line, as well as condensation in the boil-off gas return line. These valuable process diagnostic tools can help you to fine-tune the operation of your system. The meter should be installed with either the flow tubes pointing down or to the side as shown here. The meter does not require these orientations, but the meter does require that it be as full of LNG as possible. So mounting the meter in one of these two orientations helps to ensure that any vapor in the system does not accumulate inside the meter, but is instead swept through and out of the meter quickly. In the case where the meter is mounted with the tubes to the side, it is even more helpful if the flow direction is upward, as that will help with any vapor bubbles to pass through the meter as quickly as possible. Along those same lines, maintaining sufficient back pressure on the fluid in the line will also help eliminate vapor in the meter and improve the measurement that way. Any vapor bubbles that do pass through the meter will be compressed to a smaller volume fraction of the flow stream at higher back pressure. The zero of the meter can be checked using a simple zero verification tool, but it does require ensuring that the meter has zero flow passing through it during the check. It is usually unsafe to block LNG in the line to stop the flow for any length of time, so instead, the line and the meter should be empty in order to check the zero periodically. Although you can choose to insulate the meter, we recommend you do not, because the case around the outside of the meter creates an insulating environment around the flow tubes, and where the LNG is passing through the rest of the meter, a good layer of ice will typically form that acts as sufficient insulation there. You can see an example of this in the photo. Note that the ice has formed on the flow splitters and the line connections, but note also that no ice has formed on the part of the meter containing the flow tubes, where the space between the outer casing and the flow tubes was already doing a good job of insulating. As long as the piping upstream and downstream of the meter is insulated, it is usually fine to spare the cost of insulating the meter itself without having to worry about significant BOG losses. Because LNG is so cold, we recommend mounting the meter electronics away from the meter to avoid making the electronics cold unnecessarily. Because we offer meters that can be ordered with the electronics mounted directly on the meter or remotely, we can make this a simple choice with Micro Motion Coriolis meters. Here you can see a comparison of the four main measurement methods for LNG transfers that we've been discussing. As you can see, there are both pros and cons for each method. Many of these we have already covered in some detail. One of the items we didn't discuss earlier is flow conditioning. It's worth noting that Coriolis meters require no flow conditioning at all, so this can save on capital cost of the installation design as well as space. Ultrasonic flow meters do require flow conditioning, which might be in the form of either a conditioner, but more likely in LNG we will achieve this with lengths of straight run piping to avoid the risk of flashing and pressure drop across the conditioner plate. It is also worth noting here that Coriolis meters require no scheduled maintenance and do not wear out over time, so maintenance costs can be extremely low. This view helps to reveal that overall Coriolis meters present more advantages than other methods for LNG measurement. Emerson offers several different solutions for LNG terminal operations. Here you can see a list of some of the applications in an LNG terminal where Coriolis meters are useful. Liquid ultrasonic meters from Emerson can deliver all the benefits we have been discussing that come from dynamic flow measurement in the line sizes that are too large for Coriolis meters to be used. Vortex meters have useful applications in LNG terminals as well. And Emerson offers gas chromatographs or gas-specific gravity meters that can both be used to monitor the heating value of the vaporized gas samples. A live density meter is available to measure blender feed streams. Here's a view from above of a typical LNG tanker offloading station that combines storage, blending, and truck loading. Coriolis meters have applications on the jetty, in the blender, and at the truck loading rack. Vortex meters can be found in locations for boil-off gas capture at the storage tank and for liquid injection at the recondenser. In this photo, you can see a 10-inch Coriolis meter on the jetty that is used to offload ships delivering LNG to the terminal. In this case, the terminal decided to insulate the meter. Here's another view of the jetty platform. You can see in this view that the Coriolis HC3 meter is installed with the flow tubes extending downward through the platform, as recommended earlier. At the blender, there are two 2-inch CMF300 Coriolis meters installed. This is a view of one of the truck loading bays. Here you can see how a 3-inch CMF300 Coriolis meter with insulation has been installed up above the truck loading bay. This meter is used to measure the amount of LNG loaded into each truck. Okay, time for one final poll question before we go through the last section of the webinar. In this case, please select the quantity units that you use for LNG custody transfer most often. And as always, submit your answer by clicking on the Submit button at the bottom. Give everybody a chance to get their input. Okay, very interesting. There's a lot of mass measurement going on, as predicted. Fair amount of energy and some volume as well, so a good mix. The final topic we're going to cover today is around cryogenic flow meter testing and certification. Micro Motion Coriolis meters have been tested, certified, and used for Coriolis transfer legal trade of LNG and other cryogenic fluids for over 16 years now. However, the largest Coriolis meters that have NTEP certified are 4-inch meters. Some of the reason why meters larger than 4 inches in size have not yet been officially certified is because there have been no officially recognized traceable cryogenic test facilities in the world capable of testing at the higher flow rates that are needed to certify these larger meters with cryogenic fluid. The National Institute of Standards and Technology, NIST, has for many years maintained a liquid nitrogen test facility in Boulder, Colorado that could provide traceable reference measurements for cryogenic flow meter testing based on a gravimetric method. The flow capacity of this lab is sufficient to test meters up to 4 inches in size, and this has been very convenient for Emerson as it was quite close to the Micro Motion Coriolis meter design and manufacturing headquarters in Boulder. The NIST cryogenic testing facility has been temporarily out of commission so that it could be relocated to another location, the Colorado Engineering Experiment Station, known as CESI, or CEESI. CESI has reassembled and is in the process of recommissioning this facility for commercial testing with the cooperation and support of NIST and the NIST personnel who had previously operated the system. Within the last month, I was notified that the system is up and running and will be becoming available for testing again as soon as the metrological traceability has been fully reestablished and documented in its new home. VSL in the Netherlands operates a primary small-scale test facility that can test cryogenic flow meters on LNG at flow rates up to 25 cubic meters per hour, which is about 187 kilograms per minute, or 415 pounds per minute. There is a project at VSL currently underway to supplement this capability with a mid-scale facility that would increase the flow capacity by a factor of 16 up to 400 cubic meters per hour, which is around 3,000 kilograms per minute or 6,500 pounds per minute. The mid-scale facility plan will use cryogenic Coriolis meters as master meters to bootstrap the system up to higher flow rate capacities by calibrating each meter individually against the gravimetric standard in the small-scale facility. Then, by flowing through combinations of the traceable 2-inch master meters connected in parallel, a higher flow rate will be achievable. Future concepts for a large-scale LNG test facility at VSL that would increase the testing flow rate capacity by another order of magnitude, up to 4,000 cubic meters per hour, are being considered. Emerson makes use of and supports these testing facilities, and we continue to look for opportunities to expand testing capabilities of cryogenic liquids to higher flow rates than are currently possible. In addition to the special traceable test facilities that are needed to perform type evaluation testing of meter designs, there is also a need for advances in field inspection testing methods so that all the LNG flow meters that are installed in the world can be safely and accurately tested as needed by inspectors and operators to maintain a schedule of periodic checks on meters that are in service. Many operators use portable weigh scales and fuel storage tanks to perform this type of field testing today. However, this process can be rather involved and might be subject to difficulties as the weather, wind, and other ambient conditions choose not to cooperate. A better alternative for field testing of LNG transfer systems that would be right in line with the bootstrap approach that VSL is using for the mid-scale facility would be portable master meters. Emerson is working with various consensus standards development entities around the world to help develop the standards and procedures that will be needed to continue to evolve and improve field testing methods. Emerson commits resources to support consensus standards development for the LNG and many other industries. Emerson is contributing input and technical experience to support the development of 2 new annexes for the OIML R117. One of the new annexes will address LNG transfers, while the other will address marine vessel bunkering. The OIML R117 annex additions are in the first committee draft review and comment stage of development, and it is worth noting again that the CD1 does include a requirement for LNG to be measured in mass units. In the USA, the National Conference of Weights and Measures, or NCWM, has just approved the DGE units we discussed earlier, and this was done at the 2016 annual meeting that was held in July in Denver, Colorado. The content of NIST Handbook 44 is maintained through the process of the NCWM, and it is important to note that Handbook 44 only covers LNG in one section, the section 3.37 for mass flow meters. There is another section 3.34 in Handbook 44 for cryogenic liquids, but this section does not apply to LNG. LNG is specifically excluded from the cryogenic fluid metering section 3.34 because it is not a pure fluid, so the boiling point density is not set as it is for the other pure cryogenic liquids that are covered by this section. Only the mass meter section currently addresses LNG because the density is not needed to convert to mass if the meter is already a mass meter. Measurement Canada has posted terms and conditions for LNG measurement, and these also include a requirement to measure LNG in mass units. In conclusion, as growth in the world for LNG continues, more and more improvements in the infrastructure to support LNG will be needed. One very natural step in this evolution will include a transition in many custody transfer applications from static measurement methods like tank gauging and weigh scales to dynamic measurement. Emerson Micro Motion Coriolis meters offer an excellent solution for this transition with the most accurate mass flow measurement of LNG. Because Emerson has over 20 years of experience in measuring LNG with Micro Motion Coriolis meters, we are confident in our ability and experience that we can help with the LNG industry as it continues to meet expanding needs for accurate measurement. Thank you for attending the webinar, and thank you for sharing your responses on the poll questions. At this time, I'll turn it back over to Allison, and she'll lead us through the question and answer session.
Great. Thank you so much, Mark, and thank you for all the great information presented in today's webinar. As Mark just mentioned, we're going to open it up now for questions and answers. So as a reminder, please use the chat window in the upper right-hand corner to ask any questions, and Mark will do his best to answer those. And if for whatever reason we don't get to your question, don't worry. Mark will follow up post-webinar with some answers. And it looks like, Mark, we already got a couple in the queue here, so I'll turn it back to you because we got about 10 minutes or so to go through these. So
okay. Well, I see one question here is, why is flow measurement not very common in LNG cargo offloading? Well, as we covered earlier, cargo offloading is typically done by tank gauging today. And loading and unloading of large tankers that transport LNG for international trade is usually done under a large contract. And the term of those contracts will often span many years. So typically the infrastructure involved is dedicated to the execution of the terms of the contract between two parties. And for this reason, the measurement of each individual load is not always under the same scrutiny, because monitoring the average levels in storage can act as a good long-term indicator of any problems in time to sort out disputes between the two parties involved. If you contrast this with a filling station where vehicles are being owned by different parties and coming in and filling up every day, in a case like that, the accuracy of the measurement of each product transfer becomes really critical to ensure that there are no winners and losers in the measurement uncertainty, and that each individual customer receives an accurate report of the amount that they purchased. Um, Got several requests for copies of the presentation, and I'm just going to remind people that Allison will be posting a link, and so you can go back and view the webinar and listen to the recording anytime after that. That'll usually take less than a day for that to come out, so you should get that link in your email. Another question is, how much can the composition of LNG really vary? More than you might think, actually. The process of liquefying the LNG actually eliminates a lot of the contaminants and impurities that you normally expect in natural gas itself, especially a lot of the inert gas components. However, even though LNG variation is not as much as you would find in natural gas from a pipeline, you can still have a lot of variation in the amount of the different hydrocarbon molecules like the ethane, methane, and propane. In fact, depending largely on the region in which the original gas was produced, as I mentioned earlier, LNG, even in liquid form, can still have anywhere from 86% methane up to 96% methane. And the heating value as a consequence might vary by as much as 1.5% per unit of standard volume and 0.25% per unit mass. It may surprise you to know that the different regions of the world have different specifications. I mentioned this earlier, but the LNG heating values required in these different markets don't always overlap. Lean LNG with a high heating value that's lower than 1,065 BTUs per standard cubic feet is used in North America and the UK, whereas rich LNG is often used in the Far East markets that might range from 1,090 all the way up to 1,170 BTUs per standard cubic feet. So some LNG in European markets may even be as low as 990 BTUs per standard cubic feet. This is why I mentioned earlier that in some cases, blending and LPG extraction control are used to regulate the heating value so that exporters can meet the specifications of different markets, and that opens up the possibility for them to have a wider customer base. Yeah, I have a question here about with a new plant, assuming this is a gas treatment plant or a liquefaction facility, is Coriolis good enough to eliminate the need for weighing station for custody transfer? And I think the answer is yes. I'm expecting that with a weighing station, you're going to be loading trucks primarily. And since there is legal approval of Coriolis meters up to 4 inches in size, that's usually plenty to cover the loading flow rate ranges for trucks, which is typically done at about 3-inch line size. Got a question about, does Coriolis meter have internal historical logging for audit tracing? And yes, there are Coriolis meters available today that are custody transfer approved that have the ability to store a lot of data internally within the transmitter. The Micro Motion new 5700 transmitter is capable of a great deal of historical logging. And although it uses physical seal lockout for custody transfer applications, it also has the ability to do data logging for troubleshooting and also configuration file historical audit traceability. Now, here's a question about how are Coriolis meters proved or calibrated periodically after installation in an LNG application? I mentioned earlier that there's a study that's been done and documented by a third party about the transferability of the calibration at ambient conditions to LNG conditions. And how this was accomplished was by doing round-robin testing between a laboratory that calibrates at our factory using water and some of the LNG and liquid nitrogen testing facilities that are traceable through national standards. And by proving that the Coriolis meter calibration didn't change, we created a documentation of the Micro Motion Elite type meters showing that the uncertainty can be met. Now, in the field, if calibration is still needed, often this is accomplished by using truck scale. And you may load a truck and do weigh scale testing on a periodic basis as an in situ check of the Coriolis meters. That's the most common one I'm familiar with. Another option that's also available is cryogenic volumetric provers, and the Emerson Flow Daniel company has developed a cryogenic prover that can be used for this purpose as well. So we had one person state that they're interested in a truck loading application in Arizona, and they load 10,000-gallon trailers, which is right about where I've seen CMF300 elite meters used. So the meter that would be most suitable for that application is probably a Micro Motion CMF300 meter. And we have actually a pretty well-developed and sophisticated sizing tool that we use every time we issue a quotation on a Micro Motion meter in order to make sure that the fluid properties and the velocities and pressure drops are all as expected. So I would predict that that tool is going to select a 3-inch CMF300 meter for this application, but I always encourage people to go through that exercise of doing a thorough sizing so that they can have all the predictions that that tool provides as part of the decision-making process. Here's a question about FLNG. Many of you may have heard about floating LNG vessels, and there's a couple of different types. There's LNG production vessels, which are actually servicing subsea wells and producing gas. And Coriolis meters are often used on these vessels. And there's another whole category of these types of seagoing vessels called FLRU, which is floating regasification units, or FSRU, I'm sorry, floating storage and regasification unit. These are also using Coriolis meters, and they can travel to a different site and have LNG stored, which is regasified on the vessel before being delivered on shore into a gas distribution network. Here's a question about, are there any digital password protected seals on the data? Yes, you have the option for password protection on many of our transmitters, and you have additional option for protection if you order the NTEP approved version. So you can actually put a physical seal on the device in the form of a wire seal, which is recognized for legal trade devices, which goes beyond just password protection. It would limit your ability to go in and change the configuration or access the data unauthorized without physically breaking the seal. So the seal can be broken, of course, but it provides positive identification of any cases where tampering may have been occurring so that an investigation can be carried out. I think we're just about out of time. We got to most of the questions, so I just want to thank everybody again. This has been really rewarding. I definitely appreciate your participation in the 3 poll questions. And Allison, do you have anything you want to say to wrap things up?
Yeah, thanks again to Mark. And again, if you have any additional questions that you think of afterwards, or if Mark hasn't gotten to your question yet, he will get to your question. And if you think of any other ones, please don't hesitate to either email Mark or use the contact button at the bottom of your webinar console. I want to thank you again for joining us today. And as Mark said, for all your participation and your great questions. As a reminder, we are going to be sending a link to the recording of the webinar tomorrow, along with links to those additional resources. Would like to thank you again for joining us and viewing the presentation, and we hope that you have a terrific day. Thank you again. Bye-bye.
Bye.